this?
We could hear you.
You can just, okay. Okay, I'll just, yeah. Okay, so today I decided I will talk about language use and learning in embodied interactions. And just to give a preface of what kind of excites me about this general topic is that the natural habitat of language, is this on? No, it's not on. Okay, now it's on. The natural habitat of language is face-to-face conversation. There's a couple of properties of this natural habitat that are very useful for thinking about why language is the way it is. Face-to-face conversation is turn-based. So I say something, you say something, we sort of respond to each other. This means we don't have to always be super precise in what we say because it can always be repaired by someone else if necessary. And if we hear something and we don't really understand what it is and we think it's relevant towards some shared goal, then we can ask for clarification because we have this sort of flexibility of taking turns. Natural conversation is real time, so we're sort of responding to each other in real time, which means we don't have a lot of time to plan what we say or interpret what other people say, unlike something like writing. This also means that as we speak, we can observe and adjust to our audience's reactions in real time. So I can, see how you're responding to my talk and try to elaborate if it seems like people are confused or whatever. And then a third key property is that it's jointly embodied. We know that there are things that we both perceive because we're in the same space. And we also know that there's fundamental differences that we're never going to be able to fully bridge because we take different perspectives. We have different views of the world. We can never be in exactly the same body. And so I think all three of these properties are really special and we don't really consider them when we think about modern language technologies. And I think one of the missing pieces that we're losing when we're not looking at this is there's so many interesting things we do with language in this natural habitat that don't really show up when we just think about text on the internet. They do in, sorry?
What about prosody?
Yeah, prosody is another great example, right? Yeah, there's so many other things here that come through. Yeah, anything related to the fact that language in its natural habitat is a continuous operation rather than discrete tokens. Yeah, prosody, gesture, so on. Okay, so my work often focuses on language use in jointly embodied interactions. And because of these different things, different properties, for example, we know that we don't share the same perspectives, so we use language to bridge those asymmetries. So I might think you know something that I don't, so I'm going to try to ask you for information. Or maybe I don't understand what your perspective is like at all, so I want to resolve that by asking you a question about what you see. We also know that our actions influence the same shared environment if we're jointly embodied. So we need to plan and coordinate our actions so we don't run into each other or do redundant stuff. And this also means that at a higher level, we need to negotiate what we're going to do. For example, if we have a shared goal, deciding how to break it up into different pieces and then choose what I'm going to do and what you're going to do. And we also know that language is what allows us to do these things effectively. So we use language to also change this process. We learn how each other uses language, which might differ from our own. Maybe you say something in a different way, and I'm going to have to pick that up. We can also form new communicative conventions, so we can start naming things differently. We can establish different expectations in ephemeral expectations about how we're going to talk about the situation at hand. And in general, we can use language to carve out and craft new conceptual spaces, which then become a linguistic object that we can exploit to do these other things. And I find that really, really fun to think about. Okay. So today's talk, I want to talk about what kind of things do we do with language in something that's more like its natural habitat. And we'll look at a game environment. So this isn't face-to-face conversation, but it is real-time voice-based communication in a jointly embodied scene. So we'll talk a little bit about the kinds of things that show up. And the case study that I want to focus on here is spatial reference as it arises in jointly embodied interaction because you're in the same space, but you have different perspectives. So we'll talk about multi-perspective reference games, which is a very small sort of atomic version of the kinds of spatial reference that show up in the Portal corpus. And then we'll talk about some opportunities for actually learning to use language in these kind of jointly embodied interactions, both from just success of language use and also from observations of how the other person in our interaction is understanding the language we use. And then finally, I want to close by talking about some very recent work where I'm asking, like, what do we actually want out of language technologies? I'll talk about this data set that we have called Digital Coach, where we're looking at how people interact with each other in sort of tutoring dialogues for software systems, which is another sort of natural habitat of language use. And then I said that I had these 2 talks. I'm happy to talk about the hot takes talk offline if you're interested. OK. So who here has played something like Portal or heard of Portal? OK. So it's this generally this like very fun puzzle game that is from like 2007 to 2011 from Valve, where you are in this fantastical world where you can place basically wormholes in various spaces to solve various physical puzzles. And in the 2011 version of the game, there's a co-op version where you and another person work together to solve these puzzles. And the puzzles are super well designed. It's just a very, like, people at Valve know how to like design these kinds of games. They're like really fun games, really fun puzzles. You have to work with the other person to succeed. And so we were like, OK, what kind of things do people do with language in order to play this game together? So we have this Portal 2 dialogue corpus. If you're interested, the link is up here. All the videos are public, and you can submit a form to get access to the audio because that's behind like PII stuff. So we have 12 hours of gameplay, 21,000 utterances. There were 36 total people, and we have information about not only like what they said, but also exactly what they saw, and the actions they actually took as well in the game. So that allows us to like replay the games too, so we can do things like ray casting to find what objects were in view at any given time. So I'm going to show a couple of clips, and these ones are going to highlight this spatial perspective taking phenomenon. So there's lots of other things people do in this corpus, but because I want to focus on spatial perspective taking, I'm going to talk about this. So here we have 2 different people. On the left is the orange player, and on the right is the blue player, and you're seeing the first person perspective. And then in the bottom, you're seeing what each of them is saying. So I'm going to turn up my sound, and hopefully people can hear it.
Okay, sorry. Yeah, go back right. Yeah.
Right.
Oh, is right? Wait, hold up. What direction is right to you?
This way.
Okay, go left. Okay, and then keep going left.
Left.
Yeah.
Oh, okay. I see.
And then stop there.
OK, so something really interesting happens in this like very short clip, and we illustrated this a little bit. So the orange player, who is this taller robot, says, go right, go right, go right. The blue player moves to the right and sort of asks for clarification, like, oh, this is right. And then orange realizes that there's an ambiguity here over what right is, because actually orange wanted the blue player to go the other way. So then orange explicitly asks, what direction is right for you? And in order to answer the question, the blue player actually has to move left first and then move right to demonstrate what they meant by right, which is their egocentric right. And then orange is like, OK, that's the convention we've established, so instead actually go left. So then they laugh, and then keep going left. Blue accidentally goes right in response to this, and then corrects themselves and says, oh, left, like my left, and then confirms this is the convention they've established because they're facing each other. And there's this ambiguity over what right and left mean. And this just happens like in 10 seconds. It's super, super cool. So this is one example of this spatial perspective taking where they both see each other, they know which way they're facing, and the ambiguity is over whether right is your right or my right, basically. Are we taking an egocentric perspective with respect to the person in the puzzle, in the maze up here, or with respect to the person who's giving the instructions? But in this kind of environment, there are more complex versions of spatial relations that show up because these rooms are so complex. So here's a different dyad. Again, we have the blue player on the right and the orange player on the left.
I see. Oh, okay. I see. So I can step on this, and then you can head back through the portal, and then walk. And then you can walk through the door on the right, I think.
Oh, let me see. Yeah, this one opened.
Okay, so orange player, when they said you can walk through the door on the right, has no idea which way the blue player is facing. So now they can't take advantage of knowing the gaze of the blue player. They have to use, like, this spatial relation on the right is built instead on this sort of sense that there is a room in here with two doors, probably, and they're on a wall, and probably what makes, even if I don't know exactly which way blue is facing, blue also doesn't know, blue also knows that I don't know which way they're facing, and so the reasonable sort of point of reference might be the wall with the doors on it. So if I say the door on the right, and we both know that we actually can't see each other, then the best frame of reference is the wall with the doors. And that works, right? There's no real ambiguity over this.
Okay.
And then, have you tried placing a portal yet?
Sorry, doing what to a portal?
Placing a portal. So you can use your left and right click to shoot out.
Oh, yeah.
Yeah, and then you can do that on those white walls. So to your right.
Oh, these walls. Okay.
Yeah.
Okay, and so here where orange says to your right, the response from blue is turning to the right to see the walls, which were actually behind the blue player when to your right was said. So again, this isn't based off of the first-person view of what is on the left and right in my current field of view. It's more referring to what direction the blue player should move in.
And then there's one more in the room you were just in.
This one?
Yeah. To your right.
Yeah, and again,
Oh,
orange is taking advantage of this fact that orange knows the layout of this back room here. And once blue enters the room, it's no longer a question of what blue is actually looking at. It's more indexing into this sort of higher level map of the environment that orange thinks blue shares with them, is in the common ground. Okay, so this is just to illustrate that there's all sorts of really interesting spatial relations that come through in this jointly embodied scene, precisely because not only are we in the same environment, but there's actually different types of occlusion where we could see each other, but we might not see each other. And we're just as language users, we're super flexible to this. And I think these kind of phenomena are super cool. But in order to study this more empirically, we're going, and quantitatively, we're going to design studies that sort of elicit very specific kinds of this phenomenon. So the last couple examples you saw, we haven't yet sort of designed an experiment that elicits those precisely. Instead, we're focusing on the case where you can actually see each other. You can know which way your interlocutor is facing. So even in this case where we're standing static and we know which way we're facing, this is also challenging. Language grounding requires taking into account the other person's perspective. So you're obviously looking at me in this way, and so I can decide to say that I'm moving to my right, and then that that means that it's my right. But for you, it looks like the left. And this sort of accommodation, as an alternative, I could say, look at the screen on your left, which might be that one, and now I'm accommodating you because you don't care what my perspective is anymore. I'm sort of giving you a reference that lets you just use your own frame of reference. And this is accommodation where I am changing the words that I use to just accommodate whatever your perspective is. So there's a lot of older work on this from cog-sci literature and linguistics literature looking at how people do this in very synthetic scenes. So we might have a game where okay, here's a table, there's two objects, you're here, your partner's here, how would you refer to this one? And it would be the one on the right, or the one on my right, or the one on your left. So there's different ways you can configure this. And so we're going to study this in a similar task called a reference game. So that was a reference game, an example of a reference game. So I'm just going to, as an aside, talk about what we mean by a reference game, which allows us to study very specific language phenomena sort of in a lab environment. So as a generalization of this kind of task, or this kind of game, we have two players, two agents. We have a speaker that maps from an observation to a natural language reference. So we have some observation O. We have a set of possible referents. I think Yoav mentioned reference games in his talk yesterday. So reference are the things that could plausibly be referred to. And then we have a target, the identity of the target that you're trying to refer to if you're the speaker. And then we also have a listener whose job is to take Oh, and then this gives us we want a referring expression, which is a natural language expression, describing the target with respect to the whole scene. And then the listener's job is to take their observations from their perspectives, the set of possible reference that they believe are possible to refer to, and the observation of the speaker's utterance, and then produce a distribution over what the reference are. And so in order to measure the success of this kind of game, we sample first an utterance from a speaker model or a person. This gives us a natural language referring.
What do you mean by target? I mean, it seems like going right, going left is a continuous thing. It's
Yeah. So we're not talking anymore about action. We're just talking about the thing on the left or on the right. Yeah, and I'll show an example really briefly. So. Right, so we have the speaker is conditioned on a target, so we give them a target. We're like, OK, this is the thing you need to communicate to your partner. You get a referring expression, and then the listener just takes the referring expression and then their observation of the environment, and then guesses what the target was. And we're successful if we get if the listener chooses the same thing that the speaker intended. So one example of this, and this is coming from a data set we had a couple years ago, is we have two different views of an environment. So if I'm the speaker, this is my perspective. I can see my listener in the back. If I'm the listener, this is my perspective. I can see the speaker right here. And then there's all these little things that I can refer to. In this particular case, the set of reference are these spheres. So that's the only thing that we could plausibly refer to. Like if someone said, the ceiling fan, that would be invalid for the game as we defined it. And we indicate to the speaker what their target is. So there's 3 spheres. The speaker sees one of them is blue. That's the target. The listener only sees 3 red spheres. They don't know which one is blue. And so the task is like describe where the blue sphere is to the listener. So what the speaker does is they take this view. They sample a referring expression, so like on the right near the basket or on your right near the basket. And then the speaker's job or the listener's job is to take this this referring expression and their view of the environment, and then select one of the 3 spheres that this most likely describes. So if they select this one down here, then we can measure success as whether, from the global view of the scene, whether the listener selected the blue sphere. And here they did, so success. OK, so this is just to sort of set the stage both for what is a reference game and also the precise environment that we're working with. So we have a data set that has a bunch of these scenes and then has human written referring expressions that are really like the main point of this particular data set that we had at EMNLP is this multi-perspective reference game. Yeah.
My feeling is that for this particular game, the language component is quite minimized. It's mostly about special kind of orientation.
Well, so it's what we want to do is look at how people use language with respect to a very specific feature, which is the spatial orientation.
I'm thinking that if you make a mistake, it's not because the instruction was not correct, maybe, but just because it's a challenging thing to.
Yeah, I mean, I guess there's this question of like, what is it like? Is perspective taking part of language or part of just reasoning or something? But it's definitely necessary for producing language, and so this is what we're sort of. I'm like ambivalent about whether we call that language or. I mean, it's at least exposed via language or tested via language, because we have this intermediate X language representation. OK, so. So we have this data set that I showed you, and one of the questions is, OK, well, I'll just say, language models are really bad at this particular task because they don't take perspective, right? You show them the speaker's perspective, and they describe things with respect to like the sort of pixel layout of the image rather than the layout of the scene, or even what's even more useful would be with respect to like taking the perspective of the listener. So how do we get models to be better at this? We're going to try to learn from communicative success to improve models at generating references. And the motivation here is that if we say something and we observe what the response is from our listener, we can learn something. It tells us something about what our listener interpreted as what we said, even if we didn't mean what they thought we did. So the setting here is that we're going to take our model, and in this case it was like llama, We're going to sample a bunch of references for about 200 scenes, so 200 different referring expressions from llama. And then we're going to show people the referring expressions from llama and the listener's perspective, and then they're going to do the reference game. They're going to try to select what are the spheres that are being referred to. And we experiment with a bunch of different rewards to say, OK, given this sort of observation of listener comprehension, how do we improve speaker models at speaking, generating referring expressions?
No clarification, like asking.
No clarification in this case.
Like a one round of
It's one shot. Yeah, yeah. And yes, I mean clarification is like we're really trying to minimize the phenomenon here. Yeah. So in general, so here I'm showing we have the communicative success rate. So on held out scenes, how many referring expressions that were generated are understandable by people. So if we take the same scenes, a random referring expression is going to give us a third chance. For the baseline model, which was an older lava model at the time, there was like 60% communicative success. GPT-4o was like 66. I'm asking my student this week to rerun the numbers because this is a little old. And then human performance for human written references evaluated by human listeners is like 91%. So we experimented with a couple different rewards. One is that in this game, if the human listener selected the right thing, then we give a positive reward to that example, and we throw everything else out. So if the model generated a referring expression that was wrong, we just ignore that data. And we do see improved performance over the lava baseline, which is good. But we wanted to try a couple other things. So we don't want to just throw away these negative examples. We can still use them, because even if the human chose something that wasn't intended, that still tells us that that's the meaning that the human found in that referring expression. So we can actually use what the human selected as the positive example, like the positive intent, paired with the machine-generated referring expression. And when we do this, we get slightly higher performance. But then we thought, OK, well, maybe what the human selected isn't the best reference, but we know it's at least better than what the machine was told to describe. So let's just have this maybe more contrastive loss, where we say that the utterance that was observed should be more likely if the user selected for the target that the user actually selected than for the target that was intended in the model. So then we use this as a reward. And we get even higher performance than the GPT-4o at the time, just with 200 fine-tuning examples. We also see that this influences the style of the referring expressions too. So for all of this is I think probably still true today. Vision language models are extremely verbose. By default, GPT-4o gives us 79 tokens per referring expression, which is way too long. Humans write about 16 in this task. And we can reduce this with our learning from our different losses, but the one that gets us closest to the human and basically equivalent to the human lengths is this sort of contrastive loss, where we're trying to pair the referring expression more with what the human selected than what the machine was conditioned on. OK. So this is learning from communicative success, which is essentially just, did the human select, what did the human end up selecting compared to what was intended? But there's other things we could learn from. And one of the things that we've been exploring learning from is the actual incremental process of language comprehension. So when we think about these referring expression games, as I am generating a referring expression, there's some work in psycholinguistics that suggests or proposes that as I'm generating a referring expression, I am simulating what you might do as I'm generating each word. And I'm trying to target your attention. So the generation of my referring expression is an attempt to guide my visual search process. So if I say the black box, the first word I say is black. So you might go to the teapot, but it constrains the space. And then when I say box, it takes you down to the actual black box. And we don't actually explore this in our work, but as the speaker is producing the referring expression, they will check the listener's gaze as a form of feedback, incremental feedback. So the question here is, can we actually learn from these patterns of gaze during reference comprehension? And the first thing we do is we train model that estimates human gaze. We don't collect gaze data ourselves because it's very hard to do. We tried to experiment with doing this on a web browser, but it just does not work. So we take an existing corpus that pairs human written referring expressions with human gaze scan paths, and then we basically train this model that says, given like a prefix of a referring expression, where would the human look? We get better performance than the baseline that proposed this data set and model. So this is just something that we're going to use later in our actual learning algorithm. So what we end up doing for learning is we have this iterative learning process where we are generating referring expressions using our gaze estimator that we just trained to see where the human might have looked for each of the words in that referring expression, and then use this to construct some training data for optimizing our referring expression generation policy. So we deploy our speaker policy in a new image with a new target. During training, we sample the human estimated gaze, and then we're going to experiment with a number of different rewards based off of these gaze paths. And I don't have time to go into complete details on all of these. We just tried a bunch of different possible things. And our baseline is from just a non-gaze listener that just says, OK, given the referring expression, what would I have selected? We also simulate an iterative gaze-like listener from a base VLM as well. And then we evaluate on a number of held out data sets. And what we care about both is the communicative success rate. So how often did the model generate an unambiguous reference that a human could understand, and then also the sequence length. We don't want their references to be super, super verbose. So when we look at some of these results, here I'm showing across these there's 4 different data sets: the circle, the diamond, the square, and the triangle. They're just different kinds of referring expression data sets. Human data is this gold data, so we're very close to perfect communicative success, and also have very, very short referring expressions. The base model, base VLM, Molmo, has extremely long referring expression, very, very long referring expressions and lower communicative success. So we experiment with our different rewards, and we find that the ones based on gaze, which would be the red and green here, and then these 2 different blue ones, both decrease the length of the sequences and also, in some cases, increase the communicative success rate. And the models that are learned from the non-gaze feedback would be like these ones. We see increased communicative success, but at the cost of very, very much longer referring expressions. So there's this always this trade-off between the two that we're still exploring. And so when we look at some of the actual examples, so on this one, the target object is this bowl in the bottom left. The default model says a white bowl with a red border containing a brownish red sauce located in the bottom left corner of the image. The non-gaze fine-tuning gives us an even longer referring expression, and the best gaze model just says bottom left. And the human reference is bowl on bottom left. OK. OK, I wanted very quickly, well, maybe I should skip this. I don't know.
Maybe skip it.
OK. I wanted to show some cool data set we have on human coaching of complex software designed to evaluate, designed to evaluate how well models can be used to empower people as language users. But OK. Anyway, so this is my conclusion, and then many of the collaborators that I've had here. So thank you. Oh, I'm happy to, questions? Cool.
A large part of what you are saying is motivated by the fact that machines are worse than people.
Yeah.